Welcome to the Euler Project. This is episode 3. The Euler Project is a series in which we use Clojure to solve the problems on the online Euler Project, and then, just like the Mythbusters, we take them to the max. In this episode, we're going to take a deep dive into the topic of prime numbers, just for fun. The third problem in the Euler Project simply asks us to find the largest prime factor of 600,851,475,143. Now, if you've seen any of the videos on cleancoders.com, you've probably watched me do the prime factors kata a number of times, either in Ruby or in Java. This time we're going to do it in Clojure, and of course, we will use test-driven development. We begin, of course, by creating the most trivial test we can, the most degenerate test we can. Let's see that if it can find the prime factors of 1, which, of course, is the empty set. And so to pass that, we'll just return the empty set. And that passes. So then we try the next most obvious case. Can we factor 2, into a list with just a 2 in it? And of course, the way to solve that is to check to see if n is greater than 1, and if it is, return a list with a 2 in it, otherwise return the empty list. And of course, this will pass. Then, of course, we attempt to find the prime factors of 3, which is just a list with a 3 in it. And in order to get that to pass, we do a cute little trick. If n is greater than 1, we just return n. and this passes. The next test is to find the prime factors of 4. And that, of course, is a list with 2 2's in it. And to make that pass, we have to do something fairly horrible. If the input number is divisible by 2, that's what this particular form does. If that's true, well, then we just concat 2 with the factors of n divided by 2, or the quotient of n divided by 2. So we've got a little recursive algorithm going here. Okay, well, that passes too. So next we try the prime factors of 5, but that just passes right out of the gate. And so does the prime factors of 6, which are 2 and 3. Right out of the gate, that passes. So this algorithm looks like it's, well, close anyway. And if we try the factors of 7, well, that works too. We appear to be on a roll here. I mean, even 8 passes. To get 9 to pass, we have to generalize our algorithm a bit. We need to, instead of checking for division by 2, we have to check for division by the divisor, some divisor, and we need to be able to increment that divisor in a loop. But other than that, it's not a big change, is it? And that passes pretty well, too. Well, okay, so now let's just try a whole bunch of prime numbers. We'll just multiply a bunch of prime numbers together and see if we can factor them out. I expect that this is probably going to pass. And it does. And so now we can plug in the Euler problem and see what the factors are. The test should fail and tell us the answer. And it does. And the answer, the largest prime factor of 600,851,475,143 is 6,857. Cool, right? And what an elegant little algorithm this is. The recursive algorithm takes three arguments: the list of factors, which starts empty, the number we are factoring, which starts at n, and the current divisor, which starts at 2. If n is not greater than 1, then it must equal 1, and the algorithm is over, so we return the factors. Otherwise, if our current n is divisible by the divisor, then we recur with the divisor added to the factors, n divided by the divisor, and the current divisor. Otherwise, we recur with the current list, the current n, but the incremented divisor. Now think that through a few times and convince yourself that it works. Of course, this algorithm has a little bit of a flaw. I mean, it works just fine if you give it relatively small numbers that are easy to factor. But if you give it a really big prime number, well, let's just watch and see what happens. So let's try this on a pretty large prime number here. This is the Mersenne prime 2 to the 31st minus 1. Let's just see how long this takes. It's still working on it. Still working on it. Heavens. I think that's going to take a fair bit of time. How long will it take? Okay, well, I just finally had to stop it after about 2 minutes, so this is taking too long. The problem, of course, is that increment statement sitting down there. That increment is going to force us to try out every divisor between 2 and 2 to the 31st minus 1, which is about 2 billion divisors. But you know what? 2 billion really shouldn't take that long. So let's instrument the algorithm and see what's going on in there. All right, so I added this little doohickey here. It's just going to print something every 100 million divisors, right? So that ought to give us a kind of clue as to how long this whole thing's going to take. Let's run it and see. Oh, there we go. All right. So there's 200 million. Let's see. Let's count it out. 1002, 1003, 1004. Okay, so 4 seconds for 100 million, and we're going to have to do that 14 times. What is it? No, it's about 2.1 billion, isn't it? Let's see. Let's do that math. Let's see. 2 to the 31 is, 2. So it's going to have to do that 21 times. So 4 times 21 is about 2 minutes. Yeah, I probably should have stopped it a little too early. Here, I'm going to fast forward and you can watch it go. But it should stop right around 200 or 2.1 billion, right? So yeah, let's just watch it. Oh, there he went. Well, that's peculiar, isn't it? I mean, it should have stopped by now. So, something's going wrong here. I wonder what it could be. Have you guessed what the problem is yet? It's in that highlighted area of the test. It's that call to math pow. Math pow returns a double. And you know, mixing integers and doubles can be tricky sometimes. You see this form right here where it's comparing the modulus for 0? Well, if the mod function returns a floating point 0, this is going to fail. And here I can show that to you. It's pretty straightforward. Here I've got a REPL set up here, and here, look at this. Equal 0, 0.0. Okay. And false. Yeah, so I think that's what our problem is, isn't it? I guess that's one of the downsides of using a dynamically typed language, isn't it? Anyway, it's a pretty easy problem to fix. We'll just replace that math pow thing with an integer there. That's going to fix it. And let's just see how quickly it goes now. Okay, there we go. Let's see. There's 200 million. There's 300 million. Ooh, that looks like it's a lot faster, isn't it? Of course, you know, integer math, so it would be a lot faster. Let's see. 1001, 1002. Yep, 2 seconds. So it's twice as fast. That means it's going to take, what, 42 seconds to get to the end? So let's, well, here, I'll just speed it up and we'll get to the end. Okay, we're getting close now. Let's see. It ought to finish. Oh, yeah, there we go. Okay, so yes. All right. It did manage to find out that the only prime factor was, in fact, 2 to the 31st minus 1. So, you know, it's a prime number. Great. So back to the problem at hand. This is slow, but there's an old trick we can use to speed it up. Given some number n, an integer, and some other number f, also an integer, which is a factor of n, then n over f is also a factor of n and also an integer. And either f or n over f is going to be less than the square root of n. You can prove that to yourself if you want, but it's trivially true. Which means, of course, then, the limit of our search is not n, it is the square root of n. All right, so that looks like this, right? We've got this cond here instead of the if, and the condition we're looking for is whether the divisor is greater than the square root of n. And if it is, then we just say that the remaining n is the last factor. We stick that on the end of the list and we return. Otherwise, the algorithm's exactly the same. And I made one other change here. I created this power2 function, which gives me a power of 2, and you can see how that got implemented here. A little bit of an interesting way to do it. Anyway, let's just run this. We're going to see how fast it goes. There we go, and what did that take us? 13 milliseconds or something like that. Not too bad, huh? Not too shabby at all. Let's try a bigger factor of 2. All right, here's 2 to the 61st minus 1. Let's see. That's another one of those Mersenne primes. Let's see how long that takes, huh? Well, looks like that's going to take a little bit longer. I wonder how long. It should really just have to count up to 2 to the 31st, because that's kind of like the square root, isn't it? So we thought that was going to take 42 seconds, so this might take 42 seconds, I suppose. Oh, only took 26 seconds. Actually pretty doggone fast. Not bad at all. Huh. But what about prime numbers themselves? What algorithm can we use to calculate a nice long list of prime numbers? 2,200 years ago, a man by the name of Eratosthenes of Cyrene created an algorithm to do just that. He's also the first guy to calculate the diameter of the Earth, so there's that. Anyway, the algorithm works like this. You start at the beginning. You assume that that's a prime number. And then you eliminate all the multiples of that prime number, which are all the even numbers here, right? So we're just going to wipe out all the evens. Ding, ding, ding. Okay, nice. Now, you start at the beginning of the list again, right? Which is the number here? 3. Okay, so we're going to wipe out all the multiples of 3. Well, we already did 6, but we can do 9. And we did 12, but we can do 15. And we did 18, but we can do 21. And we did 24, and that's the end of our list. So, okay, now you go to the next one. 5. Well, okay, we're going to wipe out the multiples of 5. Well, 10, okay, and 15, okay, and 20, okay, and 25. All right, we're going to wipe that out. Now we go to the next one. 7. Well, okay. 7, wipe out the multiples. 14, right. 21, well, I guess that's the end of that. All right. 11. Let's wipe out the multiples of 11. Gee, are there any? Yeah, 22, but that's already gone. All right, 13. Can we wipe out the multiples of 13? You notice a pattern here, by the way, right? We've kind of stopped wiping out multiples, haven't we? 13 would be 26. Well, we don't even go that far. 17. So all the unmarked numbers are prime. That is the sieve of Eratosthenes. Implementing this algorithm in Clojure is pretty straightforward. We begin down here with this getPrimesUpTo function, which is just really a simple guard clause that makes sure that we don't try to get the primes up to -24 or something like that. It calls the sieve function where the real work is done. Here's the sieve function, takes the upper limit, that's the last prime we're going to get, if it is in fact prime. And this is just a simple recursive loop. It begins by initializing the candidates list to a list of all the integers from 2 up to and including n. Right? The range function is an open interval on the end, so you have to increment it if you want to include the last. And that gets pumped into a function here, this intset function, which derives from this library here, which is a nice handy little library that allows us to have sets and maps and things like that of nice fast integers. So that's what I need. I need a set of integers here because the sieve of Eratosthenes is in fact a set arithmetic problem. All right, so I've got the set of all the candidates here. And if that set is empty, then we must be done. And so then we're going to return the primes. Notice that the primes are initialized here with the empty list. So hopefully by the time the candidates are empty, we will have accumulated a significant list of primes. Then we loop, and we loop by removing the multiples of the first of the candidates. Now, initially that's going to be the number 2, but then every time we're done with this, the first in the candidates ought to be a prime number. Well, we're going to remove all the multiples of those prime numbers and pass that back in here. So then the candidates will be all the numbers with the multiples of that first prime removed. And we will take the prime number, the first in the candidates, and we will add that to the list of primes. That's the whole sieve right there. Now, how do we remove the multiples of the first? Well, that's up here. Pretty straightforward. We're going to take the list of candidates. We'll get the first candidate out here. That's actually going to be a prime number, right? And then we're going to calculate all the multiples. And the multiples are very straightforward. It's just another one of these integer sets, which is calculated by ranging the first candidate all the way up to the last of the candidates and adding the first candidate. So we're going to step through by first candidate. That'll give us all the multiples of the first candidate. Then we use the set difference function to subtract all the multiples from the candidates, and those are the new candidates that we return. So there's the whole sieve of Eratosthenes right there. Now let's just see how well this works. Let's go start up a REPL here. And we're going to run it. Oh, heavens. Get primes up to 100. Let's do that. That's nice, isn't it? We got a nice little list of 100 primes. Let's calculate how much time it takes. So time of get primes up to 1,000. Let's do that. Yeah, okay. And, oh heavens, how long did that take? About 7.7 milliseconds. So that's pretty good. And do these numbers look prime to you? They certainly look prime to me. I mean, my eyeball is a prime number sieve. Yeah, okay, fine. Let's try that again. Let's do 10,000. And you know what? Let's not print them this time. Let's do this so that we don't print the primes. Let's get that over here. Yeah, I think that'll work. And that should just give us the time. Okay, so, to get 1,000 primes took us, 5.3 milliseconds. Let's get 10,000 primes. Let's see how that works. And that took us 132 milliseconds. So, all right, and let's get 100,000 primes and see how long that takes. And it's going to take a little time, isn't it? Okay, 7.8 seconds. Of course, I've got the video recording software running, so that slows it down a little bit. Tell you what, let's do 1,000,000 primes. And this is liable to take a bit of time, so I'm going to just fast forward and see how long this takes. So I'm not going to make you wait for this. Look at the time up on the upper right. It's 9:35:01. Well, okay, I think I've waited long enough here. What is that, 7.5 minutes? So I'm not going to wait any longer for this. Just too long. Just took too long. I don't know why it took so long, but okay. It took too long. Okay, yeah, that's pretty slow. So maybe using set arithmetic was not such a great idea. In fact, maybe using Clojure's persistent data structures, fast as they are, maybe that wasn't such a great idea either. Maybe what we should do is use good old Java's mutable arrays. Using Java arrays isn't very hard. This is how you make a Java array. Right? It's the make array function. It's going to make an array of Booleans. And it'll make 1 plus the number of elements. We ignore the leading 0 in the array. So let's just walk through the algorithm because it's pretty straightforward. You remember the initial guard clause down here. That hasn't changed. The sieve algorithm starts by creating an array of composites. Right? This is our Boolean array. If we're going to find all of the primes up to 100, then we're going to create an array of Booleans whose last index is 100. That's why we increment n here. The array is an array of Booleans, and the Booleans stand for composite numbers. So they're true if the number is composite. They are false if the number is prime. Of course, the array gets initialized to all false, so the initial assumption is that all numbers are prime, and then we mark the multiples as true, and that's how we run the sieve. Okay, next is the limit, and the limit, of course, is the square root of n, so we're not going to go beyond that, and that's how we keep the algorithm moving fast. And then here is the sieve algorithm. It begins with a loop, and we begin with the candidate initialized to 2. Now, if the candidate exceeds the limit, then we're done. And we filter the primes. What filtering the primes does is it just takes the array of Booleans and turns it into a list of prime numbers. So that's all that does, and I'll show that to you in a minute. If we have not exceeded the limit, then we get the composite at the candidate index. So we're asking, is this composite? And if it is composite, then we just skip it. We recur and do the next candidate. But if it's prime, well, then we're going to mark the multiples. We're going to mark the multiples of that prime, and then we will recur by incrementing the candidate. So we just do the next candidate again. All right, so that's the basic algorithm. Now, how do we mark the multiples? Well, that's up here, and that's fairly straightforward as well. All right, we're just going to pass in the composites and the prime and n. And remember now, composites is a mutable array. So we're going to be making changes in that array, and those changes will be seen in the other functions that we've been working with. So, all right, we're going to loop, and the loop initializes I to be twice the prime. So that's the first multiple of the prime. And so long as I is less than n, we're going to continue doing this. And we're just going to set the index I of the composites to true, and then we recur with I plus prime. That's the next multiple. So we just walk down the array, multiple by multiple, setting those multiples to true. That's the whole sieve algorithm right there. And now the filter primes function, pretty straightforward. It's just a loop. It initializes primes to be the empty list. It initializes I to 2. And then if I is greater than n, we're done. And we return the primes. Otherwise, we get the array at that index, If it's true, then it's a composite, so we skip it. We just increment I and recur. If it's false, then we've got a prime, and we're going to add that prime to the list and increment and do the next one. So that gives us the list of all the primes. Okay, so now I ran this for you. I'm not going to bother to run it for you live. I already ran it. And here's get primes up to 100. And you can see it gives you a nice little list of the first 100 primes. It takes about 3.7 milliseconds to do that. And then I did it for 1,000, and it does that in 43 milliseconds, so a little more than 10 times longer. And then I did it for 10,000, and it took 377 milliseconds, so again, about 10 times longer. And then I did it for 100,000, and it did it in 3.7 seconds, so again, about 10 times longer. And then I did it up to 1,000,000, and it took 35 seconds, again, about 10 times longer, which may lead you to believe that the algorithm is linear. It seems to be very close to linear, although there is a doubly nested loop in there. You'd expect a doubly nested loop to have something like an n squared behavior, but the inner loop moves much faster. The bigger the primes get, it moves a lot faster because we're just getting the multiples of that prime. So that really shortens that inner loop. And it's just the outer loop that dominates, makes it look kind of linear. I think if you were probably to do the calculations, it would be n log n or n k log n or something. But who cares? I don't really care about those O numbers here. It's very close to linear. And this is pretty fast. So for deeply nested high repetition loops like this, it's pretty clear that Clojure's persistent data structures in particular, and functional programming in general, are probably not the right solution. I mean, when you've got serious number crunching to do, functional programming is probably not the way to go. But wait a minute. I wonder how fast this algorithm would be if we just wrote it in plain old Java. Yeah, so here it is in Java. Standard sieve of Eratosthenes. It uses a Boolean array, right? It's an array list of primes in there too. That's just at the end, right? And I mean, that's the algorithm. We start at 2, we loop, okay. If it's not a composite, then we add it to the primes. Otherwise, we mark the multiples. And very simple. I mean, that's a lot easier than the Clojure one, isn't it? Well, okay, how fast is it? And I did that here, but you should look at the tests first. The tests are pretty interesting. The initial tests I wrote just make sure that I am, in fact, getting prime numbers. And then I said, well, give me the primes up to 1,000. And I happen to know there are 168 of them, so I checked that out. And then I said, okay, get me the primes up to 1,000,000, and I happen to know that there are 78,498 of those, so I'm kind of trusting that. And let's do that 1,000 times. So let's calculate all the primes up to 1,000,000 and do that 1,000 times. And how fast does that run? Well, first of all, you can see that the tests pass, right? You see that down here. Test pass. Okay, that's nice. And how long did that take? Took 4 seconds, 4.5 seconds. 4.625 if you want to be precise about it. So that's a lot faster than Clojure. That was pretty impressive, wasn't it? I mean, that Java algorithm was 10,000 times faster than the corresponding Clojure algorithm, even when it was using Java arrays. I mean, as fast as Clojure is, and by the way, Clojure's pretty fast. It just can't compete with a raw Java or maybe even a C implementation, especially if you've got really tight loops and you're doing lots of little tiny fiddly bits things. Does that mean that we should entirely abandon Clojure for problems like this? Well, not quite. You see, Clojure interops pretty easily with Java. Let me show you what I mean. So here I've created a new Clojure function named fastPrimesUpTo, and I'm going to call the Java program. And I've rewritten the Java program slightly so that it's now in a package inside of a class. and the name of the function is primes up to. So it's in the lowercase sieve package, and it's in the uppercase sieve class, and it's the static method primes up to. Here, let me show that to you. There it is. This is the sieve package here. Here's the sieve class. Here's the sieve method and the primes up to method. And the primes up to method calls the sieve method and so on. Same method that we just saw a few minutes ago. So this is really simple. And oh, by the way, you should notice the project Clojure file for Linigan. The way you do that is you just tell it where the Java source code is, and it automatically compiles the Java source code and links it in with your Clojure project. So what that means is that Clojure can just call Java trivially. And so I did that down here. You see I've got a little statement down here in the REPL. So I'm going to call fast primes up to 1,000,000. And I'm going to suppress the output by just sticking it into X. And then I'm going to do that 1,000 times, and I'm going to time it all. And of course, that took 5.2 seconds. So you can see that you can greatly speed up an algorithm if you choose which parts to put in Java and which parts to put in Clojure. In this case, we didn't put an awful lot in Clojure. All we've got is this one function here. Although that allows us to then manipulate things nicely. And by the way, we're going to look at some other uses of that in just a few minutes. So here are the prime numbers between 1 and 100 in order. Now what I want you to notice is that there are a lot of instances of consecutive prime numbers that differ by 2. 3 and 5 differ by 2. 7 and 11 do not differ by 2. 11 and 13 differ by 2. 13 and 17 don't, but 17 and 19 differ by 2. 23 and 29 don't, but 29 and 31 differ by 2. And 37 and 41 don't, but 41 and 43 do. And 43 and 47 don't, and 47 and 53 don't, 53 and 59 don't, but 59 and 61 do, and 61 and 67 don't, and 67 and 71 don't, but 71 and 73 do, 79 to 83 don't, 83 to 89 don't, and 89 to 97 don't. Now these pairs are called twin primes. They differ by 2. There's a very famous conjecture in mathematics. It's called the twin primes conjecture. It posits that the number of twins is infinite, that no matter how far you go down the list of prime numbers, you'll always find another twin. So let's investigate this a little bit. Let's come up with an algorithm that finds twins for us. Finding twins is pretty straightforward. We're just going to take a list of prime numbers right here. Then we're going to loop through that list of prime numbers to compile a list of twins. Now, this is pretty straightforward. If the count of the number of primes is less than 2, then we're done, because there can't be any more twins if there aren't at least 2 primes. And so we're just going to return the twins. Otherwise, we're going to compute the difference between the first and second primes, and if that's equal to 2, we've got a twin. And if it's a twin, then we recur with the twins getting the first number added to it, and with the rest of the numbers, of course. And if it's not a twin, then we just say, okay, well, recur with the current twins and the rest of the numbers. That's really it. That's the whole algorithm. And pretty straightforward to try this algorithm. Here, let's find all the twins up to 100. So find twins of the, fast primes up to 100. And we're going to get, okay, those are the twins. Notice that it only puts the first element of the twin. So 3 is a twin of 5. That just happens to be an accident. 5 is a twin of 7. 11 is a twin of 13. 17 is a twin of 19. It only puts the first element of the pair of twins into the list. So that's the twins up to 100. There's a few of them. And let's find the twins. Let's do it the easy way, Bob. Let's find the twins up to 1,000. Oh, good. And there's several of them, so there's a lot of twins, twin primes up to 1,000. Here, let's change it a little bit more, and we'll just say count the twins up to 1,000. That's nice, isn't it? And there's 35 of them. Okay, well, let's do 10,000. Okay, so count the twins up to 10,000, and there's 205 of them. Huh. Well, okay, let's count the twins up to 100,000, and that's oh, that took it a while. Now, that's actually kind of strange. I mean, why did it take so long? I'm only scanning through 100,000 numbers here, and well, how long did that take? Let's just time that. Here, once again, Bob, do it the easy way, right? I'm going to change that count into a time. There. Okay, so that took. Forgot to. So I'm just going to put a time in front of this whole thing, and let's see how long it takes. 1.8, 1.9 seconds, something like that. That's a very long time for just 100,000 elements. So I know Java's faster than Clojure, but Clojure's not that slow. So something funny is going on here. What could it be? And look up here, and there's nothing really very bizarre about this algorithm. But what are we operating on? We're operating on the result of fast primes. Well, here, let's do this. Let's say def primes equals fast primes up to 100,000. Okay. And then we're going to say time def x find twins of primes. There. Okay. So that should count the time. And we should get something like 1.8 seconds. Yeah, okay, fine. All right, now let's do this. Let's say def primes get primes up to. This is the old Clojure algorithm that was so slow, right? Okay, that's not the Java one. Yeah, it's slow, all right, but we're not measuring the time for this one. We're measuring the time for the find twins. So here we say find the twins, and bingo, that was fast, man. That was 5 milliseconds. So it's got something to do, the timing issue here has something to do with what fast primes up to is returning. Now, what is it returning? Wow, here's that Java program. It's returning a Java array list. And a Java array list, once you start pumping it into things like first and second and rest, well, God knows what the devil that's doing. There's probably all kinds of horrible code in there. So let's do this. Let's just turn this into a vector. We're going to just turn that whole thing into a vector. Let's see, what have I done wrong here? Yeah, okay, got to get that. Okay, if we turn that into a vector, that'll just scrape through all the primes out of the array list and turn it into a Clojure vector. All right, well, let's try that. I'm going to exit out of the REPL and line REPL again, go back into the REPL. Okay, so now let's say def x or def primes fast primes up to 100,000. Nice. Good. That gives me my primes. And now let's say time the count of find twins of primes. Oh, well, that's really fast, isn't it? So that's what it was. That was what our problem was, right? It was dealing with an array list coming out of the Java program. And obviously, if you're working in Clojure, it is much more efficient to use Clojure data structures. Okay. Well, then let's just keep right on going here. Let's go on and say, let's replace this with find twins of fast primes up to a million. And how many of those are there? Right? And, oh, piffle, I forgot a parenthesis, didn't I? Okay, that took us 36 milliseconds, and there's 8196 of those. Okay, let's do, let's go to 10 million, shall we? There, that should be 10 million. Is that 10 million? Dude, yep, 10 million. Okay. Okay, good. Took 320 milliseconds. That's pretty interesting. There's 58,000 twin primes, 59,000 twin primes, all the way up to 10 million. Gee, let's go to 100 million. Let's go to 100 million. Yeah. Do. Whoa, okay, that took 4 seconds, but okay, there's 440,000 twin primes up to 100 million. Wow, pretty cool. I wonder if twin primes get rarer and rarer as the numbers get larger and larger. Are they distributed evenly amongst the primes, or do they get more tenuous as you get out towards the number line's bigger parts? So I wrote a little program to work that out. I calculate the fast primes up to some n. This is in a function called twin density. So I get all the primes up to n, and I count the number of primes. Then I get the twins, and I count the number of twins, and then I just do a little bit of math here. The prime density is the number of primes divided by n, and the twin density is the number of twins divided by n, and the twin prevalence is the number of twins divided by the number of primes. And let's just see what that looks like. You can kind of see it down here. I've got up to 1,000. There's 168 primes. There's 35 twins. The prime density is about 1.68. Well, you can tell that because that's 168 and 35, 3.5%. Yeah, 35. And the twin prevalence is roughly about 21%. So 21% of the prime numbers are twins. Let's try this up to 10,000. See what happens. Okay, well, looks like the numbers are decreasing. The prime density has gone down a little bit. The twin density has gone down a little bit. And the twin prevalence has gone down a little bit. Let's try it up to 100,000. Okay, well, yeah. Looks like that's still getting rarer and rarer, huh? We've got a lot of primes and a lot of twins, but the density is down, and the prevalences are down. So let's do 10 million. How about that? Let's do 10 million. Okay, yeah. Densities are down, right? And the prevalence is down. So apparently twin primes get rarer and rarer as we head outwards along the number line. So this is pretty interesting, isn't it? I mean, we've got a super fast Java algorithm that calculates prime numbers for us, and then we can feed them straight into Clojure and do interesting manipulations in Clojure. Okay, so twin primes seem to get less and less dense as the magnitude increases down the number line. So that implies that the gaps between those twins must be increasing. Let's look at that. So I just added this find longest gap function here, and I'll print that down here, the longest twin gap. So that's the longest distance between two twins. And find longest gap's pretty straightforward. We just map the difference between consecutive twins into the gaps, and then we apply max to the gaps. So that'll give us the largest distance between two twins, and you can see the effect down here. We've got twin density of 1,000. Well, the longest gap is 150, and if we go up to 10,000, that number should get larger, 210. And if we go up again, that number should get larger. It's 630. So clearly the distances between the twins is increasing as you would expect. So this business of gaps is kind of interesting. And now I'm interested in the gaps between consecutive primes, not just twins. So let's look at that. Let's measure the distribution of the gaps between consecutive primes. So it was easy to add a few little things here. Like here I'm getting the gaps between the primes now instead of the twins. And here's the mean gap between all the primes. That's just the average, right? The average gap. And I'm getting the gap frequencies. That's interesting. You're going to like that, the gap frequencies. I'll tell you what that is in just a minute. Notice that what I'm pumping in there is the output of the frequencies method of Clojure of the gaps. That's actually does kind of a histogram calculation. Okay, and then we count the number of primes, and we get the twins and the twin gaps and the longest twin gaps, and all that stuff is the same. And then we print it all out, and we print the frequency graph from graph frequencies. Now, the frequency graph is just up here. And I'll let you look at this if you want to. Just take a chat. Notice it's you doing a little bit of log math here because otherwise the graph wouldn't look very interesting. It would have too much dynamic range to it. But otherwise, you can see what it's doing. Just walks through all the data points and draws a bunch of stars. So let's just see the output of this. And I'll let you go back to this code and look at it later if you want to. But let's take a look at the output because the output's kind of fascinating. Here is the output for the first 1,000 primes. And okay, there's some interesting numbers here. The longest gap between primes is about 20. The prime density, we already knew all that stuff. The mean gap is about 6. So they're pretty close together in general, the prime numbers themselves. And here is the distribution of gaps. Now that's really interesting, isn't it? There seems to be this clustering effect here. There's the first 3 where we've got the gaps of 2, 4, and 6. Would you be surprised to know that most prime numbers are 6 apart? Look at that. If of the gaps, the most common gap between prime numbers is 6. I mean, if you had a gun to your head and somebody gave you a prime number and told you, give me the next prime number, you'd do tolerably well to just add 6. Hey, let's do this for more than 1,000, huh? Let's do this for like 10 million. All right, so twin density of 10 million. Okay, let's see what that gives us. Okay, well, it gives us a lot of noise down there. Oh yeah, got a lot of gaps, don't we? Okay. Hey, 6 is still the most common gap. Isn't that interesting? The mean gap is now 15. So even way the devil out here, prime numbers are typically within 15 of each other. It's pretty cool. And 6, it's still 6. And there's this interesting clustering. You can almost see it by 3s, right? So there's a group of 3 here, and there's a group of 3 there, and a group of 3 there, and a group of 3 there, and they seem to follow the same pattern of up, down, up. This one doesn't quite follow it, but close. Up, down, up, not quite here. But there's this pattern of 3s, and the 3 is most prevalent in that the third gap is always larger than the 2 above it. So we've got 6, we've got 12, we've got 18, we've got 24, we've got 30. Isn't that interesting? You know, people have said for years that, oh, you can't find a pattern in prime numbers. Well, maybe not a predictive pattern. But this is not a uniform distribution. This is not a random distribution. Prime numbers have a pattern to them. That's really interesting. It's cool, isn't it? I mean, there's some kind of bizarre affinity between prime numbers and multiples of 6. I wonder what other kinds of patterns we could find. For example, what could we learn about the last digit of prime numbers? Okay, so this is the last thing we're going to look at. It's all about the last digits of a list of prime numbers. And in order to get the last digit, you've got to do some cute little thing like this, right? So you get the last digit frequencies. I pump it into the frequencies method, so you can look that up. And the idea is we take the prime numbers and pass them in there, and then the base. So, the last digit in base 10, the last digits in base 2, whatever it is, that's going to be the last digit modulus, right? And with that, there's a bunch of things we can do. We can print the frequencies of the last digits, so we can go out and look at all the last digits of the prime numbers, and we can also do the consecutive last digits. For example, how often does a last digit of 1 follow a last digit of 7? How often does that happen? So you can pore over the code if you want to. Here's the URL on GitHub if you want to get the code and just study all of this. I'm not going to walk you through it here any longer, but I thought it would be interesting just to try the functions and just see what they look like. So here is the last digit frequencies up to 1,000, and notice that first of all, there's a really interesting pattern here. 1, 3, 7, and 9 are the only final digits that have any frequency at all. 5 and 2, well, I mean, it should be kind of obvious that 5 and 2 should never really appear, right? Because if it's 2, it's even, and if it's 5, it's divisible by 5. So there's only one of each of those, but the rest of them have a definite pattern here. And 7 seems to be the most prevalent. That disappears, though, if you do 10 million primes. If you do 10 million, it's a pretty uniform distribution between 1, 3, 7, and 9. So no real pattern there. Now, what about consecutive digits? Well, there we start to see a weird pattern again. This is pretty cool. Like 1 followed by 1. Well, there's some of those, but there's really a lot of 1s followed by 7s. And there's an awful lot of 3s followed by 9s. And there's a whole bunch of 9s followed by 1s. That seems to be the most common. And the least common are the equivalences, the 1 followed by 1. Right, and the 3 followed by 3, and the 7 followed by 7, and the 9 followed by 9. Those are least common. So once again, we've got this interesting pattern, and it's a fairly significant difference, right? 7 followed by 7 is much less frequent than, for example, 9 followed by 1. So patterns in the primes. How interesting. Anyway, that's Euler 3 for you. A fun little jaunt through Clojure efficiency and Java interop and patterns in primes. So I hope you enjoyed that little ditty and kind of hope you maybe learned something too. But if I were you, I'd stay tuned for episode 4 because that one's going to be about palindromic numbers. Remember, guys, Clojure on.